Good morning or afternoon or whatever it is when you're watching this video. This will be the last video I'll talk about space curves in particular about. We have just a little bit to do. There are two little program notes. The first one is a Mathematica sheet, and the other one I put up yesterday has a PDF of some of these computations that we're doing. And last time we talked a little bit about a curve and finding this unit tangent vector t of t. We've got the curve r of t given by some formula. R prime of t is the velocity. It has two components, direction and length, which we call speed, and the direction is a unit vector and is this t. So that's kind of where we're at. There's a bunch of calculus that I haven't done. I've done the geometry, but I haven't done the calculus yet. And I'm going to use a little of that calculus today, but over the week on the Friday video, the video I put out maybe Saturday morning for the weekend, I'll talk about the actual calculus. Yeah, this is a calculus class. Well, I know, but the geometry is the hardest and it's the most important. But this is calculus. It's a calculation. It's coming, Snow. Just relax. It's just fine. Well, what are you going to use today? Well, I'm going to use this. That if you have two functions of vector functions, let's call it R1 of t and R2 of t, if you have two of them and you take their dot product, what a dot? A dot product. So there is a dot product. And we know how to take the derivative of each one individually, but if you take the dot product and take the derivative, yes, then you get the following. Do you remember the product rule, Snow? I'm a goose. I know you're a snow goose, but we talked about the product rule. I have a small brain. Yeah, I know, but do you remember the product rule? I mean, can you remember how that goes? Like the derivative of the first, I remember we talked about it. Times the second. Yeah, that's it. That's it, Ohm. The derivative of the first times the second times the second. Not again, just the derivative of the first times the second. That's not quite enough. I don't know. Plus. That's right, Ohm. Plus. It's getting, we only have about 20 minutes, Ohm. Then you do it the other way around. Yeah, that's right. That's right. Show off. Well, he just remembered, Snow. It's no big deal. But that's how it works here, exactly how it works here. So this is equal to the derivative of the first, and not times in this case, but dot the second, these are vectors, plus the first, R1 prime of t, dot the second. So there is the dot product derivative formula for vector functions. So these are vector functions, like this one up here, t squared, t cubed, for example. It won't be this curve, but like that. And then the dot product of those, take the derivative, you get this. And I'll show you why this works next time. You can work it out for yourself. It's pretty clear. But I'm going to use this formula right now. So this is how I'm going to use it. T is a unit vector, which means if you take the dot product of t with itself, you get 1. So now we want to take the derivative of both sides of this equation. And the derivative of the right-hand side is 0 because it's a derivative of a constant. The derivative of the left-hand side is the derivative of the first, t prime of t, dot the second, t of t, plus the first, t of t, times the derivative of the second, t prime of t. So that gets you this. And these two are the same because you can, dot product is commutative. You can do it in any order. So this tells you that t of t dot t prime of t is 0. And if the dot product between two vectors is 0, that means that those vectors are perpendicular. Exactly, Ohm. Perpendicular, perpendicular. Yeah, exactly, perpendicular. They are orthogonal. So they are orthogonal. And in fact, we will show that t prime points in the orthogonal direction that you are curving in. So t prime of t, and I should put this in a different color. I'll put this t prime of t in green. It might be short or might be long. You don't know what the length of it is. So here is t prime of t. What you do know is that it is perpendicular to t of t, and it also points in the direction that you're curving in. If we wanted the unit vector in that direction, n of t would just be then t prime of t over its length. So this is a formula for the n of t. So I'm going to try to erase around this here, this computation. And then there is a third vector that's going to be important for us. And that is the one that is mutually perpendicular to these two. I'll put this in orange. So I've got it so that it's going to be hard to draw here. And that will be called b of t. This is called binormal vector. Tangent, normal, binormal. And they are mutually perpendicular to each other. So all of these are right angles. And in one of the Mathematica thing, I think I called it TNB. In the TNB little video that I gave you a particular curve. It might even have been this one. I computed the t, the n, and the b. We haven't computed b yet, but it's just the cross product. So in that, I computed each one of these, gave formulas for how to compute them. Because it's Mathematica, you do not want to label something with a capital letter directly. So I think I used UT. Standard is to use UT for unit tangent. V and V here. And I forget why this is standard, but this is semi-standard. Rather than to call it just B, you call it VB and not UB. And you call it VN and not UN. Why? It's a mystery to me. But this is semi-standard. TN and B are standard in regular notation. And then there are 3 little animations I did. You can mess around with these if you like. They're interesting. You can do it on other ones. But here I used the graphics package from Mathematica to graph tangent vectors. So it has arrows on it. And its coloration scheme is different than coloration in parametric plot or plot, but it's still simple. But in the first of those 3 animations, you just watch the tangent vector move along the curve. So you can see where it's pointed. In the second one, you see the tangent and the normal animating along the curve. progressing along the curve. And in the last one, you see this whole floating 3, Tn and B, floating along the curve. So the first thing I wanted to do today is to show you those 3 formulas and derive those for you, and then get in a place where you can graph those yourself. You won't have to do animations, but I would like you to be able to find those vectors and graph them. So T of t, the one we already did, is the velocity r prime of t divided by the speed, the length of r prime of t. N of t, the formula for that is t prime of t divided by the length of t prime of t. And then B of t is T of t cross product with N of t. So these are the 3 vectors that I'd like you to know. B of t, by the way, is automatically a unit vector because each of these is. And these are perpendicular. So the length of B of t is the length of the parallelogram determined by T and N, but T and N are both perpendicular and of length 1, so they form a square. And the area of that square is 1 times 1 is 1. You heard it here first. So this is automatically a unit vector. Okay. So this is what I would like you to know. I'd like you to be able to graph these. This points in the direction that you're turning. This points in the tangent direction. This is perpendicular to each of these 2. So just a very brief comment about hidden figures or AWACS planes and so on. How does this stuff work? You have let's do a plane of some sort. There it is. Here's the cockpit. And over here, the plane sees this alien object. And he wants to report where it is. How does he do it? He has equipment that found it on the radar. His T is this direction. Is a flight path. His N is perpendicular, so is this direction. And his B is perpendicular to both of those, mutually perpendicular. And so he sees this, or his equipment sees this, in terms of a vector quantity. And I'll call this A, I'll call this Al for alien. So he sees the alien at some vector, and that vector is in terms of T, N, and B. So 3, 5, and 16, he sees it. 3 miles forward, let's see, it looks like -5 miles. So 5 miles left in terms of my picture, and 16 miles up. So that's where his equipment sees this. And down here on home base, so here is home base. He radios these figures. But home base knows where he is according to its own coordinates, north, south, east, or north, east, and up are its coordinates, north, east, and up, and it sees its coordinates. So he is able to compute where this is according to his coordinates by translating this, changing the basis from this ever-changing basis, Tn and B of the plane, into his coordinates in real time. So this is the basic process of how control, the control base, sees what this guy sees and is able to tell where it is and give information about what to do. All right. Now, this is a little linear algebra that we won't be doing here, but linear algebra is really involved with this whole process in an intimate way. I ask you to take a look at projection of vectors. Vector u onto vector v. And in general, a projection, there's a length and there's a direction for any of these projections. So you can find the vector projection or the length of the projection. The vector projection is u dot v divided by the length of v. And the direction of this is a unit vector v over the length of v. Now in our case, we're going to be projecting onto unit vectors, Tn and b. So if you project onto unit vectors, then the length of v is the denominator here. And so you just get u dot v if the length of v equals 1. And the direction is simply v if the length of v equals 1. And this is the case that we'll be in. So dot product, if you're onto a unit vector, and just the direction that you're in. So let's look at the tangential acceleration. Let's first of all talk about the amount. So this tells you exactly what to do. You take the acceleration and you dot it with a unit vector in the tangential direction. And that's the answer. If you wanted the tangential acceleration vector, luminous orange, cost me a bundle. Or maybe this is luminous lime, cost me a bundle. But instead of amount, if you want to talk about the tangential acceleration vector, then it is this times t. The amount is this, the direction is t. And the same thing works with the amount of normal acceleration and the normal acceleration vector. See the amount of normal acceleration. So you take the acceleration and you take the dot product with a vector that's in the normal direction. Hey, that's the normal vector. So there is the amount. If you wanted the normal acceleration vector, so if you're being asked for a vector, then you got to multiply this by n. This is a number since it's a dot product. Okay, that's it. That's it for today. I'll see you on Friday, and I'm going to have a little problem where we do all this stuff on Friday. Work on your template. Hopefully, you'll have it ready for Friday, and we'll use that template to solve the flight of the moth. See you soon.